In the last class, we discussed the convergence of alternating series and Leibniz test, which is a test which is exclusively for alternating series. In this class, we will be discussing something different which is called absolute convergence. That is also a test which is used for testing the alternating series. So, what is absolute convergence? If the series of terms summation modulus of un converges, then the series sigma un is said to be absolutely convergent. That is, for a series summation un, if the modulus of the terms summation modulus of un converges, then the series is said to be absolutely convergent. And if the series converges, but the modulus values summation mod un diverges, then that condition is said to be conditionally convergent. So, here in this case, the students have to be very careful while taking such a absolute convergence case, because in the case of alternating series, we had restricted the terms to be greater than 0. So, for alternating series, we had the definition of alternating series like this: summation negative 1 power n un or summation negative 1 power n plus 1 un. But when it comes to absolute convergence, see an example we can show: summation negative 1 power n 1 upon n and summation 1 upon n. Here we can see that when we expand these terms, we are getting negative 1 plus 1 upon 2 minus 1 upon 3 plus 1 upon 4 and so on. So, each term is considered with the sign as well. So, that means, but in the case of alternating series, we used to consider only the nth term un only. So, un we took it as a positive quantity, and so un was equal to 1 upon n. But when we consider the alternating series, when you take the absolute values of this, we are getting that is equal to summation 1 upon n, because when you take the absolute values, all these becomes positive. So, that we have to keep in mind while learning absolute convergence. So, the definition of absolute convergence with the help of this problem can be considered as: if this series converges, then the series summation negative 1 power n 1 upon n is said to be convergent. And if this converges, but this, as we know, it diverges, and hence we can say that negative 1 power n 1 upon n, negative 1 power n by n converges only conditionally. It is not absolute convergence. So, that is the main difference between absolute convergence and conditional convergence. So, here we take on expansion, we consider the modulus value, and we take or we rearrange every term to be positive. So, here whatever is the negative terms, they all comes as a positive term when we take the absolute convergence. So, that we have to keep in mind very clearly. So, that is the definition of absolute convergence and conditional convergence, and we can see that whenever a series is absolutely convergent, definitely the series converges. So, that is a condition that we have to remember. If a series is absolutely convergent, then the series converges. So, absolute convergence implies the convergence of the series, whereas the converse need not be true. Convergence will not imply absolute convergence. So, this is called the absolute convergence test. So, whenever a series absolutely converges, then automatically the series converges, but whenever the series converges, we cannot say that the series is absolutely convergent, because we have seen some examples. as we have discussed in the previous case, negative 1 power n upon n is a counter example. And that is why the term conditionally convergent came into existence. Okay. Now, why absolute convergence implies convergence? It can be proved using many techniques. One method is by considering the Cauchy criterion for series. We can take the absolute values of the terms, and that will be less than or equal to modulus of x n plus 1 up to xm, that is less than epsilon. Absolute convergence means this is less than epsilon, so this is also less than epsilon. Like that we can use this, or like that we can prove this. So, there are many techniques available. Now, let us see this example. Test the absolute convergence of the series summation minus 1 power n upon n. So, we have already seen that this is a conditionally convergent series, because we have established by Leibniz test that this is a series which converges, alternating series which converges, but as the positive terms, or if we take the absolute values, we will be getting the series summation 1 upon n, which we have shown that it is a divergent series. And so, this example we have already done. The next example is test the absolute or conditional convergence of the series summation minus 1 power n plus 1 upon square root of n plus 1 plus root n. So, how we can do this question? We can see summation n equal to 1 to infinity minus 1 power n plus 1 upon root of n plus 1 plus root n. So, here if we put the terms, or if we put the values of n, we can see that un is equal to, it is an alternating series, because if we put the values of n equal to 1 to infinity, we can see that it will be 1 upon root 2 plus root 3. We can write this as a series 1 upon root 2 plus root 1 for the first value of n, minus of 1 upon root 3 plus root 2 plus so on. So, this is an alternating series, and so we can write un as un in this case, whenever we take absolute convergence, we take un to be the entire term. So, un is equal to negative 1 power n plus 1. In the case of alternating series test, we took un to be only that value, nth term, but here we are taking including the sign. So, we will be having root of n plus 1 plus root n, so that modulus of un becomes 1 upon root n plus 1 plus root n. So, this is now a series of positive terms. So, whatever we have learned for testing the convergence of positive terms can be applied for this series, which is summation modulus of un, which is equal to summation 1 upon root of n plus 1 plus root n. So, this is your new series, which is a series of positive terms. So, we have learned different tests for showing the convergence of this series of positive terms, like nth term test, Cauchy's convergence test, direct comparison test, and limit comparison test. So, nth term test does not give you anything here, does not give the proper answer, because nth term obviously goes to 0, but that does not imply the convergence, because we have seen in the previous example itself. So, remember that the nth term test can only be used to test the divergence actually, because it is not so helpful in finding whether the series is convergent. So, for divergence we can apply the nth term test. So, here we want to find whether this series is convergent. So, we will go for direct comparison test or limit comparison test. So, modulus of un, you have 1 upon root of n plus 1 plus root n. Therefore, we can take Vn to be, the direct comparison test is much more difficult here. So, we will take limit comparison test by taking Vn equal to 1 upon root n, because in order to cancel that maximum power of n outside, the maximum power of n outside will be root n, and so we are taking Vn is equal to 1 by root n. Therefore, modulus of Un by Vn is equal to square root of n upon square root of n plus 1 plus root n. So, from the denominator we need to take root n outside. So, when you take root n outside, you will be getting root n divided by root of n into, if you take n outside from this term, you will be getting n into 1 plus 1 upon n plus root n, which is equal to square root of n upon square root of n into square root of 1 plus 1 upon n plus 1 we will be getting, because we can take a root n from both the terms on the denominator. So, this is equal to square root of n and square root of n gets cancelled, remaining 1 in the numerator. This goes to 0 as n tends to infinity. So, as n approaches, I am writing directly. So, this goes to 1 upon root 1 plus 1. So, that is equal to 1 by 2 as n approaches infinity. So, we can see that limit n tends to infinity of the ratio of the nth terms goes to a finite non-zero value, and so both the series converge or diverges together according to limit comparison test, which we have seen in the case of infinite series, tests for convergence of infinite series. So, by limit comparison test, summation modulus of Un and summation Vn converge or diverge together. But what about summation Vn? Summation Vn is nothing but 1 upon n power half, and we have learned in the case of infinite series that 1 upon n raised to p, the series p series, will converge if p is greater than 1. So, here what is p? P is equal to 1 by 2, which is less than 1, and hence diverges. Therefore, the given series summation modulus of Un diverges by limit comparison test. So, the absolute convergence is not here. The series given is not absolutely convergent. So, once the series has failed to be absolutely convergent, we need to check the convergence of the series using Leibniz test. So, we are given summation minus 1 power n plus 1, 1 upon root of n plus 1 plus root n. Here, if you take, when you take Leibniz test or alternating series test, we need to take Un to be only this value. So, this is the point which all the students have to keep in mind. Okay. So, Un is equal to 1 upon root of n plus 1 plus root n. So, what is your Un plus 1? Un plus 1 will be 1 upon root of n plus 2 plus root n plus 1, which again we have to check which one of these is larger. So, obviously, we can see from the terms itself, we can see that when you take the denominators as such, one denominator is square root of n plus 1 added with square root of n, and the other denominator is square root of n plus 1 added with square root of n plus 2. So, which of these is larger? For any natural number we know root of n is much lesser than root of n plus 2. So, this is less than this term for any natural number. Therefore, when you take the denominator 1 upon root of n plus 1 plus root n will be greater than 1 upon root of n plus 1 plus root of n plus 2, and this was your un plus 1 and this was your un. So, you have proved that un is much larger than un plus 1. Now, we need to test the limit. Where is limit n tends to infinity? Un going to. This is limit n tends to infinity 1 upon square root of n plus 1 plus root n, because there is n or root n or whatever power of n coming only in the denominator. As n goes to infinity, the denominator becomes larger and larger, and so this goes to 0. Therefore, by Leibniz test or alternating series test, we can say summation negative 1 power n plus 1 1 upon root of n plus 1 plus root n converges. So, the given series is proven to be conditionally convergent. It is not absolutely convergent. So, that is what we have proved in this case. So, that completes this example. So, test the absolute or conditional convergence was the question. We have proved that the series is not absolutely convergent, it is only conditionally convergent. Now, the next important test that we need or that we require in the case of absolute convergence is what is called absolute ratio test. So, given a series sigma un, so remember here also we are taking the entire term with the sign as summation un. So, for absolute convergence as well as absolute ratio test, you need to take un to be the term with the sign. So, let summation un be a series of non-zero terms, and suppose that limit why non-zero, because we need to take the ratio here. So, the ratio when you take un to be equal to 0, this ratio won't exist. That is why we are restricting our summation un to be a series of non-zero terms for applying absolute ratio test. So, let summation un be a series of non-zero terms, and suppose that limit n tends to infinity, modulus of un plus 1 upon modulus of un is equal to mu, and if mu is less than 1, the series converges absolutely. If mu is greater than 1, the series diverges, and mu equal to 1, the test is inconclusive. Now, what happens in each case? If mu is less than 1, what happens? If mu is less than 1 means un plus 1 is less than un. This ratio is less than 1 means as n tends to infinity, what is happening to the succeeding terms? The succeeding terms are lesser than the preceding ones. Then only we will be getting a ratio as less than 1. So, in that case it satisfies something like our comparison test, and so the terms are getting smaller and smaller. So, there is a possibility of convergence. That is exactly what is said in the case of convergence. If mu is greater than 1, what happens? The terms are increasing. So, the positive terms or non-zero terms, if they are increasing, absolute value we are taking, so they are positive terms. Positive terms, if they are increasing and going to infinity, the series also diverges. And if the ratio is equal to 1, we are not in a position to compare the terms of the series or compare the terms of the sequence. We cannot get into a conclusion whether it is going to a particular finite value or whether it is going to infinity. We cannot say explicitly. That is why we have If mu less than 1, the series converges absolutely. If mu greater than 1, the series diverges, and if mu is equal to 1, then the test is inconclusive. So, using this test, let us see an example. Test the convergence of the series summation minus 1 power n plus 1 n square upon e power n. So, let us see the example. Summation minus 1 power n square upon e power n. So, here you will take un to be the entire term minus 1 power n square upon e power n, and so when you take the absolute value, you will get modulus of un to be equal to n square upon e power n. So, when you take modulus of un plus 1, you will be getting, I will write it in the next page, modulus of un plus 1 is nothing but, here it was n square upon e power n. So, modulus of un plus 1 we have to replace, wherever there is n, it has to be replaced with n plus 1. So, that is given as n plus 1 the whole square upon e power n plus 1. Therefore, modulus of un plus 1 upon modulus of un gives you n plus 1 the whole square upon e power n plus 1 into, actually this is divided by n square upon e power n. So, division by a ratio means multiplication with its reciprocal. So, e power n upon n square you can write. So, that is equal to e power n plus 1 is nothing but e power n into e, and so 1 e power n and e power n will get cancelled. You will get n plus 1 the whole square upon e into n square. From this term you can take an n outside, you will be getting n into or n square into 1 plus 1 upon n the whole square whole divided by e into n square. So, this n square and n square will get cancelled, you will be getting 1 plus 1 upon n square whole divided by e. So, as n tends to infinity, limit n tends to infinity, un plus 1 upon un, the absolute value, is equal to limit n tends to infinity of what we have obtained now, 1 plus 1 upon n the whole square by e. So, as n approaches infinity, 1 by n goes to 0. So, this 1 plus 1 by n the whole square goes to 1. So, this limit is nothing but 1 upon e, and what is e? E is the Euler number, which is 2.71828 and so on. So, e is nothing but 2.718 etc., which is an irrational number. So, 1 divided by this number is obviously less than 1. So, what is our conclusion? We have seen that a series summation un converges absolutely if the limit goes to a value which is less than 1. So, by the absolute ratio test, this series converges absolutely. So, that is how we solve this problem. Now, why do we learn absolute convergence and conditional convergence? See, if you have an infinite series, the terms of the series are starting from n equal to 1 going up to infinity. So, for simplification of calculations, in some cases we may be required, it may be required to rearrange the terms of the series. So, the terms of the series can be rearranged without affecting the convergence or the sum of the series only if the series is absolutely convergent. Otherwise, the rearrangements may lead to absurd answers. So that is the most important reason why we are learning absolute convergence. The terms of the series, the terms of an absolutely convergent series can be rearranged without affecting either the convergence or the sum of the series. So if a series is not absolutely convergent, we cannot possibly rearrange the terms without affecting the sum. So that is the main importance of learning this session. So we have seen so far sequences, series and their convergence and divergence, and these are some of the properties that we have to discuss whenever we learn how we can manipulate with the real numbers in real life. Thank you.